The first example that we saw of the method of undetermined coefficients was pretty straightforward. We looked at y prime minus 2y, and we made it equal to a polynomial, to x plus 2. But what if things were a little bit more complicated? What if we had over here on the side, say, sine of x? The instinct is to say, well, if we follow the same rules, the same concept, then we can take y is equal to just sine of x, or some constant times sine of x, and hope that when we take y prime minus 2y, we can solve for this. But if I take y as a constant times sine of x, then y prime is going to have cosine in it. And so I'm going to need to get rid of that. Well, if I want to get rid of it, then the only place to get rid of it would be in the y itself, so now y needs to have a cosine as well. So y will have some constant times sine, some constant times cosine. When I take its derivative, that's going to have both sine and cosine as well. Okay, so let's pause and see what that looks like. We'll have a times sine of x plus b times cos of x. Y prime is going to be a times cos of x minus b times sine of x. Well, that works out. It's sort of a closed system. Every function that we have over here shows up over here. And so anything that we're trying to balance out, anything we're trying to get rid of, we should be able to manage to get this done. So that is how we bring up the method of undetermined coefficients. When we have a more complicated function, sine of x, an exponential perhaps, anything out of the ordinary, we make sure that our function over here has not just the function that you're looking at, but also that the derivatives and possibly second and third and fourth derivatives, however many you might end up needing, that they're all going to be able to cancel out. We want to have the function in such a way that when we take the derivative of sine, we have cosine, well, y itself might be able to cancel that out. And then the derivative of cosine, if it was something different, if it brought in tangent, then we would want to put in a tangent over here as well. We just want to keep going until all of the functions show up in such a way that we can clean them up. The only function we don't need to worry about is the sine of x itself. Whatever's on the right-hand side, it can show up in the function y, and it doesn't need to show up in the y prime, because we'll be able to solve for it. So that's the expected. But every now and then, of course, things get a little bit bizarre. The entire method of undetermined coefficients requires practice. Once you get comfortable with it, it's very straightforward. But it takes a bit of time to get used to what exactly is it that we put over here. So there are going to be example videos that are going to give you a sense of it. There's going to be plenty of work that can be done and lots of examples from the book. And you work with it and you get a sense of how do I define this function, and then the rest is arithmetic, right? Because now all I need to do is take a times cos x minus b times sine x. That's y prime. I subtract from it 2 times a sine x plus b cos x, and I set the whole thing equal to sine of x. Throw everything over together so that you can collect all of the like terms. Sine x, I'm going to have a negative b over here. I'm going to have negative 2a over here. And then this guy coming over will give me a negative 1 times sine of x. I'll throw the cosines to the other side, and what I'm going to end up with is negative a plus 2b times cosine of x. If a constant times sine of x is equal to a constant times cos of x for every x, the only possibility is for both of these constants to be equal to 0. So that gives us negative b minus 2a minus 1 is equal to 0. Negative a plus 2b is equal to 0. Not exactly written out in the ideal way, but it's still easy enough to solve. Probably substitution. It's easy over here to isolate for A, or from over here to isolate for B, and you substitute the one into the other. My personal preference is take A is equal to 2 times B and substitute it into, see at this point I fall back on my linear algebra reflexes. Let's label these equations 1 and 2. So substitute it into equation 1, and we have negative b minus 2 times a. So we will have negative 5b minus 1 is equal to 0. b is equal to negative 1/5, and so a is equal to negative 2/5, and therefore the particular solution, right? This is the important bit. We are solving for just a single value. The particular solution is going to be negative 2/5 sine x minus 1/5 cosine x. If I wanted to get the complete solution, then I take the homogeneous solution, c times e to the 2x, which we've seen before, and I'm going to add to it the particular solution right over here. 2/5 sine of x minus 1/5 cos of x. And that's going to be the complete solution for any possibility. They're all going to give me the same thing. And now keep in mind, just because we're using the method of undetermined coefficients doesn't mean that it changes what happens with initial value problems. If we're then given that we want y of 0 to be equal to 0, then we go over here, we plug in for y of 0, we have x is equal to 0, is equal to 0, so the value for y is equal to 0, plug that in over here, and we solve for c. Notice, this guy is not 0. Right? It's going to give us something different. So let's have this as a separate bit. So y of 0 is equal to 0. Imagine that that was the condition that we're given. Then that tells us that 0 is equal to c times e to the 0 minus 2/5 sine of 0 minus 1/5 cosine of 0. E to the 0 is just equal to 1, and so we have c is equal to 1/5. Plug that in, and we have the particular solution.